Okay, so we'll go back to another video. So here we would like to find a following closed form for the following given product series of the gamma function. So we have k is equal to 1 all the way up to n minus 1. So it's a partial product of gamma of k divided by n. So in the past, I actually did a similar video where instead of it was a different gamma representation series, but it's also we had a finite upper bound. So it's a little bit of a different computation, but if you want to check that out, the link's in the description below and attached to the cards. But throughout that process, it's a little bit similar to what we're going to be doing because we'll actually be utilizing Euler's reflection formula. And then going a little bit from there, we're actually going to, write out the expansion how it should be, for product series, then do a little bit more of an in-depth analysis on how we can actually write some things. Specifically, we'll be actually using a special type of polynomial representation to utilize the whole simplification of finding this nice little closed form. So everything that needs to be said and done, so let's actually just jump right in. So Euler's reflection formula, of course, this is defined everywhere except for the integers at n. So we have gamma of n times gamma of 1 minus n is equal to pi divided by sine of n times pi. So with this, what we can do is actually do a similar substitution. Instead, I'll call this gamma of r divided by n, and I've just replaced this for the new gamma reflection, the new Euler reflection formula, so 1 minus r divided by n. So it doesn't matter like what the numbers you choose, it's actually going to represent as a rational, so it's actually fine from there. That's simply just going to equal pi divided by sine of, now we have pi times r divided by n. So with this, let's actually put out some expansions that we can do with. So for example, let's say that we start with r is equal to 1. So gamma of r, or gamma of 1 divided by n, and then multiply with gamma of 1 minus 1 over n, simply just equal to pi divided by sine of pi divided by n. Next, let's do something with 2. So gamma of 2 divided by n, then times gamma of 1 minus 2 divided by n, simply it's just going to be just pi divided by sine of 2 pi, then divided by n. Let's keep going with a few more numbers. So let's actually try r is equal to 3. So gamma of 3 divided by n, and then multiply with gamma of 1 subtract 3 divided by n, simply it's just pi divided by sine of 3 pi divided by n. Okay, so we get the gist, just keep going on so so forth. So now, and of course we have that if we go all the way up to r divided by n, then we have this form. So now let's suppose that we actually do a substitution, we'll let r equals n minus 1. So in turn, so that means now n minus 1 for here, substitute this, so I have 1 minus 1 divided by n, and then that's the same thing in other words as n minus 1 divided by n. Then if I put this for the second term, so that means I'll have times gamma of 1 divided by n, simply it's just pi divided by sine of pi, and then just that's factor out times n minus 1 and then divided by n. So with this, let's actually put everything together. So we're actually, everything has been taken in terms of, multiplying all the gamma functions together. So with this following expansion, so we have pi times 1 divided by n, then times pi, or excuse me, gamma of 1 over n, and then times gamma of 1 subtract 1 over n. So let's do for 2, so gamma of 2 divided by n, then multiply with gamma of 1 minus 2 divided by n, gamma of 1 or 3 divided by n, then times gamma of 1 minus 3 over n. Then we keep going on so forth. So if we do something for n minus 2, so that means I have gamma of 1 minus 2 divided by n, and then multiply with gamma of 2 over n, and then now yielding us with just pi with the n minus 1 term. So gamma of 1 subtract 1 over n, and then multiply with gamma of 1 divided by n. As you see that we actually have, double the copies. So in other words, this is a nice way of saying this is everything squared. So gamma of 1 over n, then times gamma of 2 divided by n, times gamma of 3 divided by n. Keep going all the way up to gamma of n minus 2 divided by n, and then gamma of n minus 1 divided by n. And then all this being, well, that's actually, I wrote that as a parenthesis, so it shouldn't be brackets. So all that in parentheses, quantity square. So all that's left is that if we actually expand this out, this is exactly what's inside of our product series, inside the quantity square. So in the end, we're gonna actually have to take the square root of both sides of something. But what does that come down to? Well, we'll get to that eventually. So we put everything back together with everything for the pi divided by sine value. So I have pi times sine of pi divided by n, then multiply with pi divided by sine of 2 pi divided by n times pi divided by sine of 3 pi divided by n. Keep going on so forth all the way up to end up with pi divided by sine of pi times n minus 1 and then divided by n. So if I simplify all this out, that means everything in the bottom of the denominator is actually going to form a nice product series. But everything on the top, we have pi times pi times pi, but this goes all the way up to the n minus 1 times. So I have pi, then to the power n minus 1, and then everything is in a product series. So I'll write that as the product series, the finite, the partial product series from n is equal to, or rather k is equal to 1 all the way up to n minus 1 of sine of k times pi divided by n. We have to figure out what this is actually going to converge to, find the value of that. So here's where the nice interesting thing comes in. So what I'm going to do is we're actually going to consider the following function and then go on from there. Here we're going to consider the following. So I have x to the power n minus 1. We're going to set this equal to the product series from starting with k is equal to 0 and then all the way up to n minus 1 of x, and then subtract e to the power I and then 2 pi k divided by n. So we're actually dealing with complex numbers. So if you take a look closely, we're actually dealing with primitive roots of unity, so complex roots of unity rather. So this is a nice representation. This is what's known as the nth cyclotomic polynomial, and this is for any positive integers n. Is a special irreducible polynomial with integer coefficients that is a divisor of x to the power n minus 1, and not a divisor of x to the power k minus 1 for any k that is less than n. And so with the roots, these are the nth primitive roots of the unity e to the power I 2 pi k divided by n, where of course k runs through all the positive integers from 1 and then all the way up to n, and it's also k is co-prime to n, aka the GCD of k and n is equal to 1. So in other words, it's actually written as this nice product series expansion that you're going to see just in a sec. So with this in mind, so let's actually continue forward and notice that, of course, this isn't exactly irreducible, because what I can do from the left-hand side, I can actually factor out an x minus 1. And on that right-hand side, if I were to evaluate this at k is equal to 0, that actually comes down to a nice of x minus 1. So if I factor out an x minus 1 to both sides, well, and then they cancel out. So the left-hand side specifically we're left with is a nice expansion of 1 plus x squared plus x cubed. Keep going all the way up to plus x to the power n subtract 1, and then set this equal to the product series. So this is n minus 1, and then starting with the index of k is equal to 1, since we evaluate this for k is equal to 0, x minus 1, that's what it comes down to. Then divide that by both sides to get this representation. And so now we have that this is just x, and then minus e to the power I times 2 pi k divided by n. So with this in mind, and keep in mind that this roots of unity, this is running through between 0 less than or equal to k less than or equal to n minus 1. So continuing forward, so what we'll do now is let x equals 1. So what I'll do is that everything here, x is equal to 1. So as we notice, it's a nice little form of a geometric progression series that if I just, you do the math and then put everything back together, is that the left-hand side at x equals 1 is just going to simply just equal n. And then on our right-hand side, we'll have, of course, just the same product series, n minus 1, k is equal to 1. So we're left with 1 subtract e to the power I 2 pi k, then divided by n. And keep in mind that, of course, we know that the roots of unity e to the I 2 pi k divided by n. In other words, we know that that's simply represented as the same with Euler's formula of cosine of 2 pi k divided by n, and then add this with I times sine of 2 pi k divided by n. Okay, this is going to come in handy simply because what I'm going to do is we're actually going to take the modulus of both sides of our equation. So that means I have the modulus of n is equal to the product series, n is minus 1, and then k is equal to 1 of the modulus of 1 subtract e to the power I 2 pi k, then divided by n. So least of our worries is the left-hand side, because if you take the modulus of n, it's just easily just going to simply just be n. So problem solved from there. So now we got to deal with our right-hand side of the equation, or the modulus of 1 minus e to the power I 2 pi k divided by n. Well, not to fear here, so simply if I put this back, so 1 minus ei 2 pi k divided by n is simply written, if that's why there's a reason I wrote Euler's formula down, because that's what we're going to need, because it's distance, the modulus. So that means it's 1 minus cosine of 2 pi k divided by n, and then minus sine of 2 pi k divided by n. So simplifying out that's just a square root. So of course we take the imaginary and the real part, so we put the I there. Or actually no, because we're taking distance, so this is, actually no, because this is still distance either way, because we're actually taking the whole, so that's how I find the way it is. So we actually take the square root of our real part and the square root of the square of our imaginary part, then add those together, then to get the square root. So that means I have 1 minus cosine of 2 pi k divided by n, then square, add this with sine square of 2 pi k divided by n, and that's square. I'm gonna put that there. So of course expanding everything out here, so we're gonna get the following. So this is gonna be equal to the square root of 2 minus 2 cosine of 2 pi k and then divided by n. And then what I'll do from here is I'll factor out the 2. So what's nice is that this is gonna yield us a nice trigonometric identity to do the substitution. So we have 2, then times 1 minus cosine of 2 pi k and then divided by n, which will yield us the following identity of just 2, and then multiply with 2 times sine square of k times pi divided by n. And then if I just simplify things even further, so this is the same thing as the square root of 4 sine square of k pi divided by n. And to take things even further, this is the same thing as just 2 sine of k times pi divided by n. Then to go back forward, that this is actually just the product series of this is equal to n. So let me actually switch to a different marker. So therefore I have that n, which we took the distance of, is just equal to pi and then n minus 1. Then k is equal to 1 of 2 sine of k times pi divided by n. Then what I can do here is that to follow it up with this representation, that if I span this out, we get n minus 1 times of 2, so factor it outside, so it's 2 to the power n minus 1. Then multiply with the product series, so k is equal 1 of just sine of k pi divided by n. And greatly indeed that I'll just divide the 2 n minus 1 to both sides to get that the product of n minus 1, k is equal 1 of sine of k times pi divided by n is equal to just n divided by 2n minus 1. And then last but not least, we just go back to what we originally have over here. So let me make some room for a different marker. That indeed that this whole thing is simply just equal to pi to the power n minus 1 and then divided by, so we said that this is n divided by 2n minus 1. And if I just take the square root of both sides and, well, also get that so the 2n minus 1 is canceled from the bottom. So let's put it this way. I have so far 2n minus 1 and then pi n minus 1 divided by n. So all that's left is just take the square root of both sides. And so therefore the nice closed representation is written as 2 pi to the power n minus 1 and then divided by 2 and then divided by n to the power 1/2. So therefore indeed that our gamma representation is going to equal to this nice little closed formula over here, just like that for any n that you choose for all the way up to n minus 1. So there we have it, just like that. So yeah, that's pretty cool if you ask me.